Okay, let's start. Good morning. So today we're going to talk a little bit about these linear transformations. It's going to be lots of fun, draw things and so on, really develop this geometric understanding of matrices a little bit. And then the rest of the week, we're going to be really focusing on matrix algebra. We've actually covered most of it. The main thing that we need to cover is matrix multiplication, or in other words, if you have two rectangular matrices, how do you multiply them? We need to figure that out. But that's pretty much it for this week. So just a recap, a vector space, right? This is the more fancy way of saying the same thing. It's a space of vectors. Right? It's a bunch of vectors, but they have to be of the same type. And what is the point? The point is to think of these from a functional point of view. So you don't want to say, oh, this is a vector and that's not a vector and so on. You want to say, oh, vectors are things I can do things on, and specific things. So I want to think of them as functionally. Now what were the examples? Well, the first example of first type of vector space is this Rn, right? R to the 2, plane, R to the 3, and so on. Spaces of tuples. First example. Second example was spaces of matrices. So maybe M, let's say 1 by 1, 1 by 2, and so on. These are all different spaces, and then more generally M by n. And here the general thing is Rn for us. Now the point here is that R2, for instance, is pretty much the same thing as this, or maybe M21, 2 rows, 1 column. But somehow, once you sort of get more advanced, it ends up being useful to separate these and perhaps use different notations for the same thing. So for instance, this and this. Because once I am thinking of a space of matrices as a vector space, I'm sort of thinking of more things in a sense. But technically, this is pretty much the same thing as this. Okay. In any event, if you have two such vector spaces VW, a linear operator, linear transformation, linear function, these are all pretty much the same thing. Linear operator is a function t from V to W. Okay? It's like f of x type of a thing. But because it's supposed to be linear, you typically use like capital letters. You'll see like capital A and stuff like that. And the way I think about it is that this is supposed to distribute over linear combinations. Okay? Now what do I mean? In V, I can take linear combinations. I can scalar multiply, vector add. And I can do the same thing in W. The point is, whenever I take a linear combination here and apply T to this linear combination, I want to be able to distribute that T. So this really means this. So T of C1, V1, Cp, Vp. Right? I take a linear combo in V, and I apply T to this linear combo. I want to distribute. And what should I be able to do? I should be able to distribute over vector addition, and I should be able to sort of change the order of scalar multiplication so that this turns into this. Okay, so to be specific, for any scalars C1 ... Cp and any vectors V1 to Vp in capital V. That's one way of thinking about it. You can also separate vector addition and scalar multiplication. Instead of looking at arbitrary linear combinations, you can say, oh, it's just if I were to take two vectors, add them up, and apply t, this is the same thing as t of v1 plus t of v2. And if I were to scalar multiply some vector by some constant c, then I get to take this constant out. Okay, these are the abstract statements. Now later on, we're going to spend some time discussing vector spaces from an axiomatic point of view as well, because somehow we would like to be able to imagine things like, oh, vector space of signals, vector space of signals with bounded energy, or vector space of large language models given a certain architecture, whatever. So we would like to be able to make sense of these things without necessarily referring to these rather simpler cases. And so eventually, what I'm trying to say is that this axiomatic definition of linear transformations is going to be matched at the vector space level eventually. Okay? For now, we don't need it. And as far as I'm concerned, we don't need this also. Because here's the equation that really works. I don't care about these more abstract stuff. I want to think of a linear transformation from Rn to Rm as an m by n matrix. Okay? So curly L v w is the vector space, you see, of all linear transformations from v to w, because you can add two linear transformations and you can scalar multiply one by some constant. But the point is, okay, this is the space of all linear transformations from Rn to Rm. I'm saying this is pretty much the same thing as the space of m by n matrices. Okay, that's the equation. What does this mean in words? It means any linear transformation from Rn to Rm is an m by n matrix. So this is very important. Okay. Now, the rest of this class, I really want to unpack this. And as far as I'm concerned, the best way to really make sense of this is to focus on the case when both input and output are two-dimensional. So linear transformations on the plane. Okay? And that's what we're going to do. If I plug in n equals 2 and m equals 2, this basically says any linear transformation is a 2 by 2. Okay? And instead of writing transformation because it's longer, I just write operator. It's the same thing. Any linear operator on the plane is a 2 by 2. So now I want to focus on specific 2 by 2s and really visualize them as operators. Okay. So somehow, because we thought of R2 as the plane, and this is also the plane, so the input space is two-dimensional, output space is two-dimensional, and we figured out how to visualize vectors in R2, but somehow now we would like to visualize a 2 by 2. Okay, so a 2 by 2 should be something that changes the plane to another plane in a sense. So, examples. We're just focusing on the 2 by 2 case. Let's see. I wrote down a couple of them that I think are nice. Yeah, let's start like this. So for instance, let's say A is 2, 0, 0, 2. That's a 2 by 2. I want to think of this as a linear transformation. Okay? And the way we're going to do this is we're going to feed to this a vector from R2. Now remember, vectors in R2 is supposed to be column matrices. So it's going to be a 2 by 1. Okay? I cannot feed a 2 by 1 from the left. We're going to see later this week what this means. The only way we saw this was putting a vector here. Okay? So I write it like so. Okay? So this is 2, 0, 0, 2, xy. Now again, remember the compatibility condition. I do a little dimension count. A is 2 by 2. Number of rows goes here. Number of columns goes here. And this is a 2 by 1. Number of rows, number of columns. So when I do this, ultimately I'm going to end up with a 2 by 1. Okay? We have seen this expression essentially in the context of, let's say, linear systems on the left-hand side. We saw this to really represent, well, this is just 2x, 2y. Okay? This is matrix notation. If you want to use like a more multivariable calculus type notation, instead of xy as a column matrix, you can use x comma y and use like a function notation type of a thing. I'll write that as well. It's the same thing. So instead of writing this, you can write a applied to xy equals 2x comma 2y. You can write it like so as well. It's the same thing. Okay. Now, the point is how to visualize. Well, I'm going to plug in certain xy values and see what the output is. Right? So this is my input now, and this is my output. Maybe I should write that as well. Inputs, outputs. This is output. Well, the simplest case, I think, is to plug in x equals 0, y equals 0. When you do that, if this is 0 and this is 0, the output is going to be 0, 0 as well. Okay? So this is nothing specific about this guy. Any linear transformation is going to do that. No linear transformation is going to change where the 0 is. If you have time later, we're going to talk a little bit about computer graphics. And in the world of computer graphics, a more sort of sophisticated transformation ends up being useful, and that is what is called an affine transformation, where you allow motion of the origin also. But we're not going to do that for now. 0, 0 is sent to 0, 0. Okay, so let's write it. Fixes the origin, doesn't move the origin. Well, what I can do is I can perhaps look at vectors along the horizontal and vertical axes and see where this transformation takes. So 1, 0, for instance. Again, when I plug in x equals 0 here, and x equals 1 and y equals 0, I get 2x, 0. Okay? And again, if I were to do 0, 1, I get 0, 2. Maybe I should ask you this. How then can I perhaps visualize this transformation? Its effect. How can I? Yeah, go ahead.
Kind of like the, I guess, unit vectors in the x and y direction. You could just scale it by 2. Every vector you add would be that, but twice as long, I guess.
Yeah. So the way I imagine this transformation is, well, it fixes the origin. Everything else is scaled by a factor of 2. Okay. What I like doing is I like drawing a small box, like so. Okay. Like this. This is my input space. When I apply A to this, This was the original picture. Now it is scaled by 2. So imagine sort of holding this corner. Okay, this corner is fixed, doesn't move the origin. Fix this part, expand it by 2. So it's something like this. Okay. In a sense, this is nothing but scalar multiplication, by the way, right? I'm just scalar multiplying the vector by 2. Scalar multiplication is a linear transformation, that means. Okay, so let's make this slightly more complicated. I'm going to keep this diagonal shape. You're going to see throughout this course, this diagonal shape is very nice. Whenever you have a square matrix, you want the diagonals to be non-zero possibly. Off diagonals, this entry and this entry, you want them to be 0 if possible. That's like the best case. Okay, these are the easiest matrices to visualize. But now, let's say I'm changing this guy, the second diagonal entry, into 1 over 2. That's the next example. Let's say B, 2, 0, 0, 1 over 2. How can I visualize this?
It's going to be stretching your x dimension and squishing your y dimension.
Very nice. Okay. What is the geometric significance of this diagonal form? Whenever you see diagonal, that means it's fixing the axes. It's not sort of turning them around and stuff. X-axis stays x-axis, may be stretched or contracted. Likewise, y-axis is either perhaps stretched or contracted, but there's no sort of funky business happening. If you had 10 billion dimensional spaces, again, you have a bunch of axes. They would be preserved insofar as your matrix is diagonal. Diagonals are the best matrices, okay? And so again, let's try to do it like so. So maybe like this. So if I were to start with this, x-axis is stretched by a factor of 2, stretch, okay? But then y-axis is contracted. So this guy turns into this. Okay? Any comments or questions about this?
So in this, the output is a 2 by 1 matrix, but you say any linear operation would make it 2 by 2?
No. The input is 2 by 1, output is 2 by 1 also. The point is to visualize this 2 by 2. What is the space of 2 by 2 matrices? That's what I'm trying to visualize. So it's kind of bizarre, but like this is, it's kind of hard to say, but like the space of all 2 by 2s is all such transformations somehow. Okay. Any comments or questions about this? What if I were to use a negative number? Again, I'm going to keep it diagonals. Say I have this. How can I visualize this? It's a reflection. So you see, you're always using the same trick, okay? If you're getting confused, or if you're not used to this sort of visualization business, what you can do is you can just plug in certain values and see where the matrix takes them to, okay? Use 1, 0, 0, 1. These are the best ones, simplest ones. So, okay, let's say I get confused. C1, 0. C10. This is going to pick out the first column, okay? It's going to be minus 1, 0. This says that the horizontal arrow in the positive x direction is transformed into horizontal arrow in the negative x direction. But then you don't do anything with the y direction. So that C is indeed this reflection. Well, I guess, yeah, like so. Take this. Okay. X goes to this, y is preserved, so you flip it like so. Okay. So the starred I is going to be like so. Okay. And by the way, when I just draw this small box, B is not, or one of these matrices, is not only transforming this thing, it's transforming every single patch in this space. It's just that I'm just visualizing it this way, faster. Okay. So you can say, for instance, oh, the origin, okay, is going to be fixed. So let's say this is the triangle. Triangle goes to triangle. And then you can say, oh, this corner, which is the circle, it's 1, 0, goes to minus 1, 0, and so on. Go ahead.
So what one would, for the B example, like the 2, 0, 0, 1 half,
Yes.
before you transform it to B, what do you reference it to? Do you always reference it to 1, 0, 0, 1?
That's what I like using, yes. So we're going to call this next week the standard basis. It essentially corresponds to the fact that, I mean, we're all used to using x and y coordinates. Yeah.
The way I've always understood it, when you have these transformations, is you can think of like your first, like in this 2 by 2 case, you can think of the first column as like the 1, 0 vector, and then the second column is the 0, 1 vector, and like that's how they are changed. Is you have these.
Exactly. I mean, what your colleague is perhaps suggesting, let's match it with this linear combination business. Very good. So if I have, let's say, A, B, C, D, okay, and an XY, remember last week we talked about how this I can also write as x times AC plus y times BD. Okay? If that is the case, then if you were to plug in x equals 1, y equals 0, you're going to get only the first column, which then, from an operator point of view, from the linear transformation point of view, is where this linear transformation takes 1, 0, 2. I'll write it. So first column is where A takes 1, 0, 2. Second column, where A takes 0, 1, 2. Call where A takes 0, 1, 2. Very good. Does this kind of make sense? So everything sort of slowly, I hope, starts matching. Later on, we're going to learn how to make sense of linear transformations using different axes. So in principle, you can also track 1, 1, and 1 minus 1, for instance, if you want it. These are different bases we're going to learn. There's something called the change of basis. It's going to get complicated, okay? It is also not the case that linear transformations are exactly matrices, but for now, this is a benign lie that I think is going to be helpful. Go ahead.
I might have just missed something, but is there significance to the dot, star, and like the smiley face in the transformations?
Well, yes, because I want to signify somehow the orientation. So with this,
Like a numerical value, right?
oh, no, this is just a visual thing, okay? Yeah. So this linear transformation is not taking this and translating it this way. It's flipping, okay? Yeah, that's the significance. Any other comments or questions? Okay, let's do one more. What if I were to do 1 minus 1 here? So D 1 0 0 minus 1. Any guesses? Someone who hasn't spoken so far? Yeah.
Just flip along the x-axis.
Exactly, right? So instead of changing the x, you change the y this time. It's pretty much the same, but instead of flipping this way, you're going to flip this way. Good. That's your D. If I start with something like this, flip, now you're like this. Okay. If I were to do, for instance, minus 1 on the diagonal, say E, it does both. Okay, flips both the x and the y. If you start with this guy, somehow it flips around the origin, or reflects around the origin. It turns into this. So the star is the far there. Let me like so. Okay. Yeah.
Is there a way to do translations with these? 'Cause you
No.
can do, like,
Linear transformations, they're going to fix the origin. Okay. If you want to do translations, let's say you have like an image and you want to sort of move it here, that's an affine transformation. If we have time in week 5, I think, we're going to talk a little bit about that. It's very important as well, but we're not allowing translations for now. Okay. Origin is always going to be fixed under linear transformations. Now, here's the beauty of this matrix algebra, okay? Instead of thinking of this E, reflection this way, I can think of first applying C, start like this, flip using C, and then to this, I can apply this one to flip this way. So somehow E is the same thing as DC. So somehow, and this is going to be the matrix multiplication business that we're going to start talking about tomorrow. And so you see this pattern of dimension count works here as well. D is a 2 by 2, C is a 2 by 2. When I multiply these together, we're going to say, oh, the middle dimension get rid of, you're going to end up with a 2 by 2 again. Okay. So somehow, this matrix multiplication business is going to correspond to compositing functions, or linear transformations, say. Does that kind of make sense? And so that means that you can start perhaps with a complicated linear transformation and go backwards and perhaps factorize. We're going to talk about certain factorizations of matrices. It's similar to factoring out integers, maybe like prime numbers or whatever, 15 equals 3 times 5. But with matrices, it's a lot more complicated, factorizing. We're going to learn. Okay. Any comments or questions about these examples so far? So the diagonals are the easiest matrices to visualize. They keep the axes. X stays X, Y stays Y. If I had 3 by 3, they would correspond to three-dimensional space transformations. X, Y, Z, again, same thing would work. Okay? It's harder to visualize perhaps, but the same idea. Now we make things a little bit more complicated. I'm going to start using non-diagonal matrices. And this idea again works. If you have a 3 by 3 here, you put x, y, z, first column, second column, third column. They tell you where the x, y, z axes go to under your transformation. It's the same idea. But first understand 2 by 2s, okay? Once you understand 2 by 2s, everything else is pretty much the same but more complicated algebraically and geometrically too. Okay, let's keep going. I want to use something like this. Well, we had a bunch of reflections. What about reflecting along y equals x? This time I'm not going to give you the matrix. I'm saying I want a certain effect. This is y equals x. I want my transformation f to reflect. I told you it has to preserve, it has a fixed origin, so the origin is going to stay there. But for instance, if I keep track of what this transformation is doing to this specific image, what's going to happen is, well, star is going to stay on the diagonal, but this smiley face is going to go here, and then it's going to turn into this, for instance. I just reflected this like so.
Could it be like 0, 1, 1, 0?
Yes, very good. If I want to turn this into a matrix, this would be 0, 1, 1, 0. Why? Use this idea, okay? Horizontal turns into vertical, vertical turns into horizontal. 1, 0 has to go to 0, 1, and 0, 1 has to go to 1, 0. Okay? Does this make sense? If you want to use sort of like a transformation notation, you would write f of xy equals yx. Later on, indeed later this week, we're going to in fact match these linear transformations to row operations as well. So for instance, this really corresponds to scaling the first row by 2 and the second row by 1/2. And this really corresponds to interchange in the case of 2 equations. Okay, we're going to get there too. But let me write it. In terms of row operations, this is R1 replaced by 2 times R1 and R2 replaced by 1/2 times R2. And this corresponds to R1 and R2 interchanged. We're going to talk about this as well. And somehow we're going to define this matrix multiplication so that it's going to turn out that these elementary row operations is nothing but matrix multiplication underneath. Okay? So everything somehow is matrix multiplication. Okay? Again, I haven't defined matrix multiplication yet, but somehow we're going to define it in a consistent manner. What if I were to ask for a reflection? Oh, even before that, I want to make sure that this is clear. Yeah.
Can you explain what each of the columns does like separately? Because like if you have them both together, like it makes sense that it just flips it. But what if one of them didn't have the 1 in it?
For instance, here you had a 2.
Or just like, yeah, I guess. Yeah.
Let's do that. I want to keep this. let's do it here, G 0, 2, 1, 0. How to perhaps describe what this guy is doing visually? It's almost like this, but there's a 2 here.
It's like a rectangle, right? Like the y is bigger.
Mm-hmm.
Because even though the origin's still the same, but like the y scale bigger or like taller.
Right, so we can say, oh, to perhaps visualize this, I can just keep track of the standard bases or standard vectors. This turns into something. I'll just use 2 more colors here. So for instance, 1, 0 goes to the first column, 0, 1. 0, 1 goes to 2, 0. If this is unique length, it becomes like this. So it's a reflection like so, but after you reflect, you expand also in the x-coordinates. Very good. So it's like this. Okay. Flip. You have this picture. Now you stretch it like so. You can also think of it like this. This is first doing this and then applying pretty much something like this. You can also say, for instance, 0, 2, 1, 0 is 0, 1, 1, 0 first. And then I need to multiply. I haven't defined this yet, but we're going to define matrix multiplication, and then this equation is going to hold.
Does it matter what step you do first?
Yes.
Okay.
Very good.
So
It does. It does matter. Yes. Not in this case, but in other cases, yes. In this case, it doesn't matter, actually. Should be careful. Let me just check. No. You see, in this case, this is not quite the same, actually. If you were to first, hang on a minute. Exactly, this is not the same. Because if you were to do this first, you would be stretching it this way, so the mouth would be wider. And then you would be flipping. Okay, this, okay, that's a good point. Oh. This is not the same thing as this. And this corresponds, okay, to first stretching x, then flipping. And so instead of having this elongated face, you're going to have a wide face. Okay? It's going to be in the same direction, but it's going to look different. If it looks different, it's different. Okay? These two transformations in this order corresponds to this, not this. Wide face, slim face, okay? If this is kind of confusing to you, don't worry. I still haven't defined matrix multiplication, but once we define it, it's going to be compatible with what we're talking about. What you should think of is that somehow we have all of these transformations and we can composite a bunch of them to get like a more complicated one perhaps, but that compositing of functions or composition of functions is going to correspond to this matrix multiplication. And like your colleague mentioned AB, even when it is defined, is not necessarily going to be equal to BA in general. Okay? So this is the one thing that really complicates situations in linear algebra.
How would you define the second version where it's ordered swapped in simple terms?
You read this way.
Okay.
Yeah, so first scale the x-axis by 2, then flip x and y.
How would it be written? Like how G is written?
Good point. Well, how would we figure this out? Your colleague is asking the formula for this, right? Because I said, oh, you know, this is different than this, but in terms of matrices, they should be different too then, right? That's what you're saying. Let's call this H. I'll write it bigger, actually. This is what I'm looking into. Okay. I'm focusing on this part right now. I'll do it here. This transformation I'm calling H. In a sense, we're going to discover matrix multiplication too, by the way, when we write this. So I want to make sense of this guy. Okay? Just going to substitute H equals these two things. Just substitute it. H is supposed to be these two things put together. Okay, very nice. So I don't know this part, okay? I don't know this, but I know this. So I'm going to substitute. What is this? This is 2x, y. I don't want to worry about this. I'm just going to worry about this part. I know what this is. This is just this. But then I know this. Okay. So H takes xy to y 2x. In other words, it's this. So this is H.
So when you were saying that the order matters,
Yes.
when you were just given one matrix, like G equals that matrix,
Yes.
it doesn't matter what, you can't like do it in a wrong order, but when you're given two that are multiplied together, that's when the order matters?
Yes. Yes.
Is that just how matrix multiplication works?
Yes.
You can't-
Yes. For now, yes. Part of it is because we're feeding vectors from this side. We're going to learn later we can feed them from here as well, but we have to do something with that. For now, whenever you see something like this, you always read this side. Okay?
Can you expand like on G as well so we can see the difference from H?
So it's this. So this was H. So here is G. This was the alternative. Okay. G is the slim face. H is the wide face. Wide face example. Slim face example. Right. So you want me to go this way? Use these? Okay. So this is just going to substitute. Now we multiply. Okay. This. And you multiply these. Get this. Hang on a minute. I feel like there's an issue. Oh, yes. So this, okay. I got confused. So it's not the names you should be keeping track of, it's the places. Very good. Okay. So maybe we can write this as well. G equals nope. It's what is it? 0, 2, 1, 0. This versus this. Comments, questions? Your job at this stage is to look at a bunch of matrices 2 by 2, okay? Just focus on 2 by 2. Use like small numbers, 1, 2, whatever, and see what the effects, what the meanings of these specific numbers are. Okay? Put a minus somewhere or whatever. I'm going to do one more. Maybe a couple more actually. So we did the diagonals. These are slightly more complicated as you see when you're not diagonal, but it's still something like a reflection. So we have dilation, contraction, reflection type stuff. Another thing you can do is rotation, okay? H, I don't want to use I because I stands for 1, 0, 0, 1. Let's say J, 0, minus 1, 1, 0 this time. Okay. XY, or rather 1, 0, goes to 0, 1. Okay, horizontal becomes vertical. 0, 1 goes to minus 1, 0. Vertical becomes this way, turns this way, which means this J does this. Rotate. You rotate, turns into this. Okay. You can rotate by whatever angle you want, actually, but the formula is different. It's a 90-degree rotation. And what is it? Counterclockwise. If I wanted to rotate in the clockwise direction, I would put 1 minus 1 here. J, K, 0, 1, minus 1, 0. That's K now. Instead of rotating this way, I'm going to rotate this way. Rotates like so. Okay. There's one final type that we need to study, which is called shear. You sort of like move it this way, you sort of make it oblique. It's going to take some time for me to draw and sort of visualize and stuff like that. We're going to do that tomorrow, and then we're going to be on our way really discussing matrix multiplication. Thank you. All right, let's start. Good morning. So today I'm going to take attendance. I want to start talking about matrix algebra. We did a lot of it, in fact, but I want to sort of really focus on certain aspects. In particular, one of the things we need to discuss is this matrix-matrix multiplication. How do you multiply two rectangular matrices? Before that, though, there's a couple more things that we need to discuss. Don't worry about this for now. I want to keep working on examples of linear transformations on the plane. Take two-dimensional vectors, turn them into two-dimensional vectors. The ideas are the same in whatever dimension, but in 2 dimensions, I think looking at what is happening and trying to visualize them really helps with intuition. So we're just focusing on that for now, at least in class. First example I want to give is this is the matrix for a general rotation in 2 dimensions. Okay, so cosine theta minus sine theta, cosine theta. Okay, theta is some angle, or maybe I should say this really represents rotating by theta degrees in the counterclockwise direction. So this is rotate this way by theta angle. I'm not going to spend time deriving this formula, but maybe I'll leave it as an exercise. This is not a straightforward exercise in a sense. It requires some trig. If you're not comfortable with trig identities and stuff like that, it's somewhat harder to derive this formula. If you remember trig, it's going to be rather easy, or straightforward, let's say. Deduce the formula. I'll just give you an idea how you might try tackling this. Well, this is supposed to take any xy and rotate it by theta angle, right? And so draw something like this, a circle. Okay. If you start here at xy, once you apply r theta to it, it should land to somewhere here perhaps. Okay, so this is r theta xy. The point being is that this angle here is theta. What you need to do to deduce this formula is to relate the x and y coordinates of r theta xy to the x and y coordinates that you started with. And how do you do that? Well, this is where the trig comes into play. First, you need to transform this xy into an angle. So you want to sort of focus on this slope here. Let's call it alpha. And then you're going to use this smaller triangle, and then you're going to turn it into the larger triangle. There's some double angle formulas and stuff like that, or the formula for the sum of 2 angles, and you need to figure out cosine of alpha plus theta and stuff like that. Okay, how many of you know these kind of things? Trig formulas and stuff like that. Yeah, some of you familiar. It's not super major, super important for us. Obviously, it is related to all these things. It might also be a good idea to perhaps remind yourselves what these trig identities are, but it's not very important. You should know the formula, though. So for instance, if I were to plug in theta equals pi over 2, that's 90 degrees rotation in the counterclockwise direction. I'll write it here. So for instance, r sub pi over 2 is cosine of pi over 2 is 1. It's 0. So I have zeros on the diagonal. Sine of pi over 2 is 1. That's minus 1. That's 1. That was the matrix I gave you last time. Okay. If I had plugged in theta equals minus pi over 2, it would be rotation in the other direction by pi over 2, by 90 degrees. Okay. Any comments or questions about this? So let me just record here. Need trig identities. I'll just say trig. This requires trig. Okay. 2 more types of matrices that are important. 2 more types of transformations are shears and projections. So here's an example for a shear. For instance, I can say maybe something like this. So its shears are either lower triangular or upper triangular. In other words, you have the diagonal entries. They have typically non-zero numbers, but they could be 0 as well. But either this top right corner is 0 or the bottom left corner is 0. So it could be something like this. It could be something like this. Let's say -3 here. So these two are both shears. Just to remind ourselves, how do we visualize these kind of things? Well, it's always the rule that the first column is about where the 1, 0 goes under your transformation. And for the second column, where 0, 1 goes. The point of these shear transformations is that you see, for instance, for this A, the second column is 0, 1 itself. That means this shear fixes 0, 1. It doesn't do anything for the vertical vector, but it does something to the horizontal vector. So if I wanted to visualize this A, again, let's use our regular caricature. Okay, like so. Now, when I apply A to this, now it's going to turn into a parallelogram, right? It's going to be oblique. This side stays as is, 0, 1, sent to 0, 1. Okay, second column, 0, 1. 0, 1 stays as 0, 1. However, 1, 0 goes somewhere else. It goes to 1, 2. You see, you give some height to this horizontal vector. Specifically, you take it to this. Okay. So let's put coordinates here. These are 1, 1, 1, 1, 2. And then let's complete the picture. Here's a nice heuristic. Linear transformations preserve lines, okay? So if I'm trying to figure out what is happening to this, what I can do is maybe I can keep track of the corners, then maybe I can keep track of the edges and sort of see where things go. And so this stays as is. This is sort of lifted this way. And then I'm going to apply the same stuff. So this is 2, which means I should do this, maybe 3 here. Here's blue. Here's blue. Okay, turns into this. Okay, so that means if you see lower triangular, okay, you're fixing the vertical, you're moving the x, you're shifting, you're sliding the x coordinates along the vertical. Okay, makes sense? If I were to look at this, the roles are switched. Instead of fixing the x, now you're fixing the, or rather, instead of fixing the y, you're fixing the x. 1, 0 is in the first column. B fixes 1, 0. It slides the y-axis. Slides the y-axis in the negative direction. So it turns into this. So this was A. This is B. This is where I started. Okay, just draw it like so. Now it turns into something like this. Question, comment? So what's the idea? If you want, you can do this, for instance. You can imagine this top right corner for B to be a parameter, 1t01. Let's say B depends on t. It's a time-dependent matrix. What is happening here at time 0, this is just identity. As time goes to positive infinity, you're sort of sliding this way, this picture, right? Sliding this way as time goes to positive infinity. If time goes to negative infinity, you slide it this way. Okay? Comments, questions?
What makes those shears specifically?
What do you mean?
Like, what is the definition of a shear again?
This is the definition. I don't technically know the definition of the shear by itself, but I know that these are called shears.
Is it a shear when one, I guess, is it important that I can identify what a shear is?
I would say either lower or upper triangular for now. And I would even say one's on the diagonal, probably. Yeah, I think this is good. Let's define it like this. So if you want a formal definition, n by n matrix is shear if it has ones on the diagonal, if one's on the diag, and zeros either in the upper side or the lower side. Zeros, okay, let's write it like this. Let's use indices. A, okay? So let's say A is an n by n matrix with indices I and j. Shear if Aij is 1, if I equals j. And let's say Aij equals 0 if I is strictly less than j. That's an example. That's one way of defining it. So for instance, A11 is 1, A22 is 1. Okay, so that's the first condition. And then what is the second condition? So if I is 1 and j is 2, I'm looking at row 1, column 2. I'm saying it is 0. Okay? So using the stars and stuff like that, we can say, for instance, with 3 by 3, a shear looks like this. That's a shear, okay? If you want to be more fancy, probably you want to call this lower unipotent. Okay. Any other comments or questions? Okay. Now, here's a very important exercise, okay? We talked about a bunch of examples last time and today as well. I want you to verify that the R number for each of these were 2. Okay? R number for all of these examples that we discussed so far, for instance, for this, The R number is 2. The R number for this is 2. Okay? Projections are kind of different in that their R number is less than 2 in principle, possibly. So, important exercise. R number, which was another word for rank, right? Of all examples so far, today and yesterday, was 2. Okay, was 2. Because in this case we were only looking at 2D vectors, we could also say that these linear transformations are full rank. Okay? This is the maximum possible. Okay? This is the maximum possible for planar transformations. Therefore, we call them full rank. In 2D. Okay? I'll just erase this so as to not confuse you. With a projection, this is the final type of example, final type of matrix I want to talk about, at least on the plane. The R number possibly is less than 2. So for instance, if I were to look at something like this, right here, let's say projection. You might also hear the word projector. That's also used. So something like this. P equals 1, 0, 0, 0. This is already in reduced form, as you see. And it has one pivot. The R number of this is 1. Okay? It's a different type. But when you think about what this is actually doing, it doesn't do anything to the x-coordinates, right? First column is 1, 0, fixes the x-coordinates, collapses the y-coordinates, sends 0, 1 to 0, 0. Okay. So if I start with my standard picture, when I apply P to this, I'm going to end up with sort of like a degenerate picture, if you want. It's going to be just a sort of line segment like this. Collapses your image. Okay? Does this make sense? So I want you to associate R number, or this idea of full rank, to preserving information. When you apply this transformation, you're losing information somehow. You had an image, you collapsed it. Now you don't have it. With all other ones, we could rewind the transformation. So for instance, if I wanted to rewind, if I wanted to transform this back to this, well, I could just shear back. Okay? There's no loss of information when R rank is the maximum. If R rank is not the maximum, you're losing information. If someone gave you this, you wouldn't be able to construct this. Okay? This is very important. So I'm writing here. R number is 1. I should also say that the fact that the R number is 1 and not 0 corresponds to the fact that once you apply P, two-dimensional something turns into a one-dimensional something. Okay? So you have like a one-dimensional information. leaking info. Okay. Okay. So these are the main examples you should keep in mind. Okay. Any comments or questions about any of? Yeah, go ahead.
Is there another matrix that would work as an example for projection? Like, is there another one that would have an R number of 1 that would work?
Yeah, I mean, instead of collapsing the y coordinate, I could try collapsing the x coordinate. What would the matrix of that would be? What would the matrix of that be? Let's do this. Here's another example. Q. This time I want this Q to collapse the x coordinate. I'll just give you a second to think. This turns into this now.
Does that mean that a 3x3 matrix would describe like a cube?
Say again.
Would that mean that a 3x3 matrix describes like a cube?
You can get there too, and eventually we're going to do. We're going to talk a little bit more about the geometry. But let's just first answer this. Oh, okay, go ahead.
Can you just expand on what you mean by leaking info?
The point is this. If I apply, so I start with something like this. Apply P, I turn into this. Now, if I were to give you this, you wouldn't be able to reconstruct this. Here, for instance, if I were to give you this, and if I were to tell you, correct this, like how did I start, you would be able to rewind this A. So this is a reversible procedure if you want, even though that's somewhat perhaps dangerous to say, because reversibility is something other different. I want the matrix for this.
Yeah, that's exactly what I was going to ask for.
Oh, I want you to figure out.
0, 0, 0, 1.
Your colleague suggests the matrix should be this. Comments, questions, or agreements, disagreements? Yeah.
So those two are the only possible options that can be a projection then?
No.
That means like the ones can be like any number then? Like if
I can give you an equation that actually classifies projections. But let's first talk a little bit about this. Okay. This is indeed correct. Okay. And how do I think about it? This is the only trick I'm using. Okay. If I see A, B, C, D, whatever, A, B, C, D, that's a 2 by 2. It's a linear transformation on the plane. First column tells you where 1, 0 where 1, 0 goes. 1, 0 goes. Second column tells you where 0, 1 goes. So you can start with the matrix and figure out the geometry, or backwards. You can go backwards. You can think about the geometry, figure out where 1, 0 should go, 0, 1 should go. Based on this, come up with the matrix. Okay? And so your colleague says, oh, okay, where does 1, 0 go? Goes to 0, 0. First column is going to be 0, 0. Okay? Where does 0, 1 go? It doesn't go anywhere. I'm not doing anything to it. Second column is going to be 0, 1. This is the one trick. Okay? And this works in any dimension. M by n, doesn't matter. This is always the idea. Okay. Now, the proper definition of a projection would be that if I apply my transformation twice, it's the same thing as applying it once. So turning something on is, in a sense, a projection. If you turn something on, let's say you have on and off, if you click on twice, it's the same thing as clicking on once. Okay? So the formula for projection is p squared equals p. we're going to talk about what this p squared means. But maybe I should write it like this. P times p equals p. Applying p twice is the same thing as applying it once. Okay? So algebraically too, perhaps we can verify this, at least for this guy. And we're sort of transitioning to matrix algebra at this point. We don't quite know how to do matrix multiplication at this stage, at least formally, but at least I know that I just plug in a vector on this side and keep sort of looking at the image, right? So just going to look at this. This is 1, 0, 0, 0, 1, 0, 0, 0, xy. Okay, I did this last time as well. The point is this, okay? I don't know what this part is, but I know what this part is. It is x0. Okay? So I just focus on this part. Keep this. The other one becomes x0. Then apply again. But in order to get this, I didn't need to apply p twice. I had obtained this at first step, in one step. Okay? So more generally speaking then, I could, in the plane, take any line passing through the origin and imagine projection to it. It would take a while for me to write down the matrix perhaps, but that would be a projection. Because I know if I were to take a two-dimensional vector, compress it to a one-dimensional space, once I do it once, doing it again with the same projection is going to not do anything. Okay? Yeah.
So then is the only projection with an R value of 2 the identity matrix?
Exactly. Very good. Well, the point of this matrix algebra is going to be this, okay? This is always valid, but we're going to say, oh, these are p squared equals p. I'm just going to pretend that p is a number. Then you solve, okay? P squared equals p, send p to the other side. P squared minus p equals 0. If p was a number, I could just write it like this. P times p minus 1, or identity, is 0. So somehow one solution is 1, one solution is 0. If p was a number, this would be all. But you see, it gets slightly complicated once you start interpreting p as a transformation, as a matrix. Like formally, a lot of things are going to transfer to matrices, but we're going to need to be a little bit more careful about a situation like this. So it's not going to be in general the case that if the product of two things is 0, then at least one of them is 0, for instance. When you're doing this using numbers, that's one of the things you use. Okay. Any comments or questions? Here's a couple definitions that is in the textbook. They're rather useful. I wanted to discuss them. If I have a linear transformation, I'm going to call it one-to-one. More fancier word for this is injective. If the only solution for tx equals 0 is the 0 vector, okay, and I'm going to call t onto if for any output vector b, tx equals b has a solution. Okay. This is kind of complicated. The way you should think about these is, well, think about a matrix. In the case of a transformation from Rn to Rm. In other words, A is an m by n. Okay? I'm going to say this guy is 1 to 1 if the columns are linearly independent, onto if the columns span Rm. Okay? That's a faster way of thinking about it. Well, I write it here. I'll write it here. So a 1 to 1 means columns are linearly independent. A onto means columns span the whole output space. Okay. This is like a more actionable way of thinking about this 1 to 1 and onto property. We'll discuss these more next week. I know at this stage this kind of sounds abstract. It's not very important at this stage. Next week we're going to focus more. What I want to do is I want to switch to matrix algebra. Okay. And I'm going to tell you sort of these operations that you need to be comfortable with in different layers. Okay. And in increasing complexity. So first, whenever you have matrices, we already talked about this. You can pretend that they are vectors. You can vector add, and scalar multiply. So these are the vector space operations. Vector add and scalar multiply. More generally, you can just take a linear combination. The point always is that when you're doing these, the dimensions of the matrices that you're handling have to be the same always. You don't get to move the dimensions. Once you fix the dimension, they're going to stay. Always use same dimension, matrices with same dimension. Okay, that's important. Here's an example. Now we're done with geometry for now, for a while. I'll switch back to algebra. So say we're looking at 2 by 3s. For instance, I can do this, right? So 2, 1, 1, 0, 1, 2, 0, plus or minus 0, 0, 1, 0, 1, 0. Okay? These kind of things are valid. You see, I'm thinking of this 2 by 3, and this 2 by 3 as a vector in and of itself. And this is a linear combination of two 2 by 3s. How do I make sense of this? This is scalar multiplication. You just distribute over all entries. I'll do this step by step. 2, 2, 4, 0, 2, 0. If you want, you can just think of this as a minus 1 and distribute, but we'll just leave it as is for now. And then when you're trying to add or subtract two matrices of the same dimensions, you just add or subtract the corresponding entries. Okay? When you take a linear combination of two vectors, you always end up with a vector of the same type. If you're taking a linear combination of 2 by 3s, you're going to end up with a 2 by 3. Okay? If you want, you can allocate your memory before you do the calculations. This, 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 this. Okay? That's how you do vector addition, scalar multiplication for matrices. Okay? This is the first stage. Second stage, this is like the second operation is a class of its own in a sense. Taking transpose. In a sense, it's even simpler than this, but it's a deeper operation somehow. Because taking the transpose of a matrix has nothing to do with the numbers or whatever you put in the entries. It's all about the shape. It's a reshaping operator. Okay, transpose. If I have A, its transpose is going to be written as A to the T, taking the transpose. So if A is, let's say, m by n, then A transpose is going to be n by m. What is this operation? Rows are columns, columns are rows now.
Is that the rotate over like cross XY?
You can think of it that way too, yeah. Here's the example. So that's a three-dimensional vector, right? This is in R3. I told you writing this as a column is different than writing it as a row. When I take the transpose of this, rows become columns, columns become rows. 3 rows, now I have 3 columns, okay? Like this, you flip. If I had, say, this guy, this is 2 by 3. If I transpose, it's going to be 3 by 2. Okay. First row now is the first column. Second row is now the second column. Okay. This is not very deep, it seems, but surprisingly plays a big role. Comments, questions?
What does it mean? Like, what is the use of this?
How do I say this? Okay, perhaps I'll say this. Here's an important definition. A matrix is symmetric if it's equal to its transpose. So somehow, if a matrix is symmetric, it has some symmetry. Okay? This is one of the most important definitions in this class, actually. Matrix A is symmetric if A equals A transpose. Now, what can we deduce from this at this stage? Because taking the transpose interchanges rows and columns, certainly this has to be a square matrix, first of all. Okay? It has to be square. So n by n. What's an example of a matrix like this? In fact, I think in the first problem set you saw one, 2, 1, 1, 1. Okay. So an example for a symmetric matrix is 2, 1, 1, 1. If I flip, right? So columns are rows, rows are columns. 2, 1 stays 2, 1, and so on. This is symmetric. Okay, symmetric. I told you that the best types of matrices are the diagonal ones. If you have a symmetric matrix, we're going to see later that you can pretend that it's a diagonal matrix. This is what is called the spectral theorem. This is going to be the topic in week 10 or something. Okay? So spectral theorem. If A is symmetric, then it's pretty much diagonal. Then it's basically diagonal. Basically. We're going to make sense of this basically later. Okay? So somehow, if you have a symmetric matrix, you get to pretend that it's a diagonal matrix. It's the most convenient type. Why are diagonal matrices nice? Because they preserve the axes. Okay? So they have directions that just contract and dilate. Contract or expand, yeah. Okay. In more fancy context, instead of symmetric, you would see the phrase self-adjoint. It's in a higher level, it's the same thing. Symmetric is the same thing as self-adjoint. If your physics friends are talking about self-adjoint operators, because there's like a spectral theorem that whatever their context is doing this. It sort of simplifies the calculations underneath. This is the same thing as this. But we're not done. Here's another important thing. So this is as far as I'm going to go regarding spectral theorem, but we're going to spend a lot of time toward the end of this class. This is like a deep thing. It's it's a complicated thing, okay? As opposed to the theorems in the first couple chapters in the textbook. This is the main thing. If I were to take any matrix whatsoever, then if I were to look at A transpose, somehow that's going to be something that is defined, this multiplication. That's always going to be symmetric. I'll leave that to you. Once we figure out how to multiply matrices, this is going to make more sense, of course. So no matter what the matrix is, A times A transpose is always defined. It's always symmetric. What is the significance of this? Somehow this is related to these things called the singular values. Or in applications, you might have heard of something called PCA, principal component analysis. You take your observations, put them in a matrix. Typically, it's a rectangular matrix. You can't quite do the spectral theorem business, but what we're going to do is we're going to multiply it with its transpose. Now this is square. It is also symmetric. And we're going to apply a spectral theorem to get the principal components, as they say, of the data that you have. Again, this is related to deep stuff that we're going to discuss toward the end of this class. So this eventually connects to singular value decomposition, SVD. This is one important theorem in this class. Second important decomposition or theorem is going to be singular value decomposition. Okay. So somehow just doing this operation end up being super useful. Yeah, very good point. Any comments or questions? Okay. That's a transpose. Third, now we need to talk a little bit about how to multiply two matrices. We need to make sense of something like this, or P times P, whatever. I'll just write matrix, matrix, multiply. I don't want to give the formula yet. Let's just use this trick that we were using so far. Let's just focus on 2x2s. How do I multiply two 2x2s? 2x2s are linear transformations of the plane, so I can just think of them as transformations and sort of go ahead and try to perhaps come up with a formula. I'll do this here. Now the complication is going to be that because I'm trying to come up with a general rule, I'm going to use anonymous matrices, anonymous 2x2s. So let's say A is ABCD. That's one transformation of the plane. And B is, let's say, alpha, beta, gamma, delta. These are basically the same letters, but instead of Latin, they're in Greek. Okay? So I want to figure out this. The rule is this, first of all. This is going to be valid, and it's going to be a 2x2. If I use two linear transformations of the plane, when I composite them, I should get back one, possibly more complicated, transformation of the plane. So this is going to be a 2x2. Okay, so I'll write it here. Right, so you write it like this, and the number of columns of this guy has to match with the number of rows. In this case, let's say it's C, and it's going to be 2x2. 1 minute is not going to be enough for this, but you might try calculating these four entries based on this. Sort of plug in xy here, sort of go ahead. This is going to take some time to write it out. It's kind of cumbersome, but I think it is useful. We're going to start with doing this on Wednesday. Thank you. On Friday, sorry. All right, let's start. Good morning.
Morning.
Couple of things. Today we're going to try finishing up the main discussion about matrix algebra. We're almost done. We need to discuss this matrix multiplication. We have some logistical matters that I think would be good to discuss just a little bit. So problem set 1 is graded. I'm just mentioning it for this time, but going forward, I'm just going to grade it and make it available and so on. Pretty much within a week, me and our grader. So you can see your grades on Gradescope, but also on Canvas. Now, there was some issue with Canvas access. I think Canvas decided to unenroll some people from courses yesterday. A couple of you from this class contacted me, and some other students from the other class I'm teaching also. So part of the reason why I do things the way I do is these kind of things do happen. And if they do happen, there's often alternatives I want to keep. So for instance, right now, if you have access to Canvas, you can download the PDF files. There's like buttons that you can click and so on. And also, there's a GitHub repository where I try to keep updated also with the course material. GitHub is more stable than Canvas, typically speaking. And so is YouTube, the lecture courses, the lecture videos. Yesterday, I sent an email about a couple of alternative links. Did you all get this email? OK. So were you able to access the textbook using that link there as well? Did you try? So in principle, you should be able to access the textbook, the digital copy of it, using that link, because I can, but I can't quite test if using a student account you can do the same thing. I would presume you can, but it might be a good idea to perhaps try it out next time something like this happens. What else? So if you go on Canvas, if you have access right now, or to the GitHub repository, you're going to see a new document. I'm going to write, I'm going to sort of compile a collection of selected solutions from problem sets. Typically, I'm going to be writing detailed solutions to problems I grade for accuracy in problem sets. This is so that you have some idea as to what type of an answer I'm looking for. So you're going to see we're sort of grading problem sets rather leniently. Just because you got like full credit doesn't mean that you have the full understanding of the material as far as we're concerned. Okay, so I'm a big champion, or I'm a big sort of defender of hard problem sets, but I like being lenient when grading. That means, it kind of falls on you to perhaps contact me or someone else to sort of discuss what you're actually doing or what could be sort of optimized in terms of your solutions and so on. And in the exam too, the problems are going to be similar but significantly easier, okay? Because I don't like the time constraints and stuff like that. As far as I'm concerned, exams end up testing for test-taking abilities first and foremost. So that's that. Feedback, I think pretty much all of you got the idea. So this Google form and so on. Here's the responses. It's going to take me some time to sort of digest the information here. But I think on Monday, I'm going to sort of say a couple words about this. And I'm not going to spend time for every single problem set talking about the feedbacks and so on. I just want to do it for this one time only, just so that you have some assurance that I am indeed reading your answers and responses and so on. And hopefully we're going to sort of adjust the tempo and difficulty and so on based on pretty much the average or slightly above average, let's say. Okay, so that's that. Any questions about any of this? Okay, so matrix algebra. We were saying that essentially there are three layers in increasing complexity. First layer is vector addition and scalar multiplication. What is the point here? I can take 2x3 matrices and I can think of them as vectors in and of themselves and just add the corresponding entries or scalar multiply, just like you would do with a column matrix. In other words, vector works pretty much the same way. Okay, that's the first layer. The second layer is this transpose. Somehow this is not even mathematical, if you want. It's actually reshaping in a sense. So it doesn't do anything with the entries, the numerical content of the entries, but it just reshapes the matrix. So just to remind ourselves, what is a transpose? How could I think of it? How could I describe it? Say again?
Swapping the rows and columns?
Yeah, so you start with a matrix, okay? It has rows and columns. When you take the transpose of it, now rows become columns, columns become rows. In other words, you just like flip, okay? And here's again this very important definition, or adjective if you want, symmetric. What was a symmetric matrix?
The transpose equals the non-transpose.
Okay. So it has to be square to begin with. So when you flip, you want to get back the same thing. It has some symmetry, okay? This is very important. It's very simple, not very deep, at least at this stage, but it turns out to be a very important property. Okay. So if you want to use indices, you would just write aij equals aji. That's what it means for a matrix to be symmetric, in short. Okay. So in terms of the entries. If you want to write it using the transpose, means this. Okay. So symmetric means, in particular, because taking the transpose flips rows and columns, this has to be a square matrix. Okay. If it's not a square matrix, it cannot be symmetric. Okay. It's very important again. Another thing is that when we were thinking about matrices as linear transformations from a functional point of view, the first examples we looked at were diagonal matrices. Diagonal matrices are symmetric, for instance. It's in a sense, they are the best symmetric matrices. Diagonal implies symmetric. Okay. The point of this spectral theorem that we're going to discuss toward the end of this class is going to be going backward. It's not exactly, so it's not going to say exactly symmetric implies diagonal, because, you know, the example is 2, 1, 1, 1. This is symmetric, but not diagonal. But it's pretty much like it somehow. We're going to figure out. We're going to say this guy is similar to a certain symmetric diagonal matrix. Maybe I should say star here. Okay. Now let's remind ourselves. This is sort of like a short review. Why are diagonal matrices the best types of matrices? There are multiple reasons, but what are reasons perhaps that come to your mind?
They're not like mixing the different like what am I thinking of? Like the different like directions. It's keeping them in mind. It's just like scaling them.
Very good. So if you want to use a geometric language, you would say if you have a diagonal matrix, it preserves the axes. In 2 dimensions, preserves x and y. 3 dimensions, x, y, and z, and so on. If you want to be perhaps more sort of, I don't know, engineer-like or control theory-like, you would say it doesn't mix channels. Each of these entries, you could say, is a channel, x channel, y channel, z channel. Diagonal means doesn't mix these or sort of combine them somehow. Okay. Just to remind ourselves, we mostly thought about 2-dimensional 2x2 matrices. But for instance, if I were to look at something like this, D equals 1, 2, minus 1 on the diagonal. If I want to think of this as a transformation of the 3-dimensional space, R3, how could I perhaps describe what this guy is doing?
It scales the y-axis by 2 and flips the z-axis.
Very good. So you see, it becomes harder to draw pictures now in 3 dimensions. X, y, z. Your colleague says, oh, this one is all about the x-axis. This transformation doesn't do in the x direction. Y direction scales by a factor of 2 and flips the z direction. So if you want, you can think of sort of like a sphere. I'll do it here. Okay. When I apply d to the sphere, what's going to happen is it's going to be expanded this way. Okay, so now it's an ellipsoid, but also turns this way. So maybe I can sort of imagine sort of I have a face on a ball, right? Now when I apply my transformation to it, flip this way and then elongate this way. So maybe it turns into something like this. Okay, and then this is why I wasn't doing 3-dimensional stuff, but yeah.
I was going to say, so when you have that -1 for the z-axis, is that like flipping it, or is it just like kind of inverting it? Like, just in this example, would the star still be on the right side if you're on the z-axis?
Good point. Let me think. You're right. Very good. It's not a rotation in this direction, but it's instead sort of, how do you even describe it? It's just like do this. Okay. So starred eye stays the same way. Very good.
You're quite the artist.
Thank you. Okay. What I drew before was not this transformation. It's again a linear transformation, but that linear transformation is a different one than this. So somehow you should imagine this sort of like a, raster, and you sort of like take this and like pull it this way and sort of like flips it. the other way around. So it's a reflection, I should say then. Reflection in the z-axis. Okay. Makes sense. And sort of like elongated it this way. So now it's like a football or something. Okay. Good. So somehow, you see, if I were to imagine this, for instance, start with something like this and start populating zeros, replace them by non-zero things. Now, they're still linear transformations, of course, but they're going to be a lot harder to visualize. Say I put, for instance, here a 3. Okay. Gets more complicated. Diagonals, though, they are the best types of matrices because of this. Easier to visualize. We're going to see in a second, easier to multiply also. So I want you to think of matrices, even when they are higher dimensional like this, as pretty much like numbers, especially if a matrix is square. Okay? So you get to add and scalar multiply and so on. And matrix multiplication too, we're going to see, works pretty much like number multiplication. The only thing, okay, the only thing that changes is the order matters now. AB is not the same thing as BA, not necessarily, in general. We had seen an example of this, but I'm going to mention it again. Any comments or questions about any of this? This is sort of like a recap of where we are. Okay? So now what I want to do is I want to try to derive the multiplication rule for multiplying, let's say, two 2x2 matrices. The idea ends up being the same, pretty much. So let's do this. I'm going to use indices this time. A11, A12, A21, A22. Okay? This is a 2x2. And then I have another one, B, B11, B12, B21, B22. I can think of these as, well, the coefficients coming from systems of equations on the one hand, or I can think of them as transformations. These are two different compatible interpretations of what is happening, or what these are. Okay. So for instance, what I can say is this. I have one plane here. Let's call its coefficient, or rather its axes, x1 and x2. Then I apply a to it. Then I go to a different plane. I'm going to call its coordinates y1 and y2. And to this, I'm going to apply in series the B transformation. Now I have z1 and z2. Okay? I need my matrix multiplication, in other words, BA, to be so that if I transform x coordinates to y using A, and then in series y coordinates to z using B, then BA should be a transformation that transforms x coordinates to z coordinates in a compatible manner. What would it mean for this to be compatible? Well, let's think about this. So for instance, I can say something like this. A11x1 plus A12x2 equals y1. Okay? Before we were writing here B, but because this itself is going to be the so-called independent variable of this new matrix, I don't want to call it lowercase b, although it doesn't matter, of course, mathematically speaking. But y seems more like a variable to me, so I'm going to leave it as is. And then I have a21 x1 plus a22 x2 equals y2. Okay? So this system is all about these two things. If I wanted the matrix notation, I would just write it like so. A, x1, x2 equals y1, y2. And this was something we discussed all the way back in week 1. We said we can write this system of equations this way, matrix form. These are the same things. Again, I'm going to look at this situation, and this time I'm going to use bij's as the coefficients on the left-hand side. Okay, that's another system of equations. That's okay. And again, in matrix notation, this would turn out to be this. Okay, much like this is the same thing as this is the same thing as this. Well, compositing AB in this order essentially corresponds to just substituting. Take this, y1 is this, y2 is this, substitute into this equation. Okay, that's what we're going to do now. This is like cumbersome algebra stuff, but I think at least for this case it's good to see. What I'm trying to convince you of is the fact that when I told you in week 1, oh, this you can write like this, and so on, you agreed to a lot of things, actually. We're just seeing the consequences of that agreement in week 1. So, substitute. So let's call this equation 1, or system of equations 1, and this system of equations 2. I'm going to substitute 1 into 2, right? Okay. Okay, let's do it. So y1 is now this more complicated thing. This is going to hurt. Now y2 is this more complicated expression. Again, b21, same expression as this, you see, because y1 is y1 here. 1, 2, x2 plus b12, a21x1 plus a22x2 equals z2. I made a mess, okay? Any comments or questions about what is happening here? This is like a basic math thing. If you see the same thing, you should be able to, so if this is a y1, and if y1 is equal to this, you should be able to substitute. That should be allowed. Yes, that's the basic idea. But of course, what do I want to do now? I want to rearrange things, because for instance, I have x1s here repeating and so on. I want to rearrange so that x1s are, ordered, or they are put together. And likewise, x2s. When you do this, you get this. This plus this. Okay. Plus. Don't forget to distribute, right? That's the first equation. I distributed b11 over this and this. There's one factor here, or rather one summand here, one summand here. And then I factored out the x1 factors.
We're just confirming the numbers, like the 1, 1, 1, 1, 1, 2. Like the
Farming them?
Yeah, like
B small numbers, B11, B12, B21, B12.
yeah, those stand for the rows and columns.
Do you disagree with the calculation? That's what matters. I don't quite know this lingo.
You're perplexed.
You're perplexed?
Why we multiply b11 first and then b12 and then b21 and then b12?
Oh, because this should be a 2, 2.
Yeah, that makes sense. Really.
Okay. Good. Very good. Now it should be correct. There is some symmetry with the indices too. There's a pattern. That's why I'm using indices instead of A, B, C, D, and alpha, beta, and stuff that I started last time. But I'm going to do the same thing here. Plus. B21A12 plus B22A22 times x, and that should be a 1, I guess. Oh, that is true. That's x2 equals z2. Okay. Why did I do this? Because again, I want to see sort of like a linear system notation. I want to think of x1 and x2 as the unknown, and z1 and z2 as the known, or the right-hand side. Okay. Just like I can rewrite this as this and that as that, well, this I can write as in matrix form also. Okay. This. And finally, we have 2, A, 2, 2. That's the coefficient matrix. Here I need to put x1, x2. And here I need to put z1, z2. Okay? And so I define the matrix product, BA, to be this 2 by 2. This is defined as BA. Why would I want to do this? Because ultimately, once I transition to matrix notation, if I'm supposed to not forget this correspondence between system notation and matrix notation, I should be able to sort of substitute systems, which means that somehow this should make sense also. And furthermore, if possible, I would like to be able to perhaps do this multiplication without referring to x1, x2, y1, y2, whatever. So it's just like clutter. I want to leave that behind. Okay? And I want to think of B as a number, A as a number, and pretty much, and compute this product, BA. Any comments or questions so far? Now, the idea is this, okay? So this is essentially the idea. If you have here Rn, Rm, Rp, now you have more equations and more unknowns, whatever, but you can do the same trick. You can still do this substitution business. And that would, again, give you this product, the formula for the product. But of course, we would rather have some sense as to how to multiply these without sort of like using these x's and y's and so on. Here's a numerical example. And in fact, let's use this example that we were talking about before. So I'm not saying memorize this is the point. Okay? But if you forget how to matrix multiply, you can just substitute and still get away with not remembering. That's the point. So I'll do it here. For instance, let's say A is diagonal with 2, 1, and B, let's say, is the interchange matrix. No? A is this. Okay? I want to compute, let's say, BA and also AB.
Wait, so you're actually like putting numbers in instead of like A11, A12?
Yes, this is a specific numerical example now.
I see.
Okay? I just write down the matrices. We figured out what this product should be before using our geometric intuition. Now the point is to do the same calculation using algebra. They have to match. Okay? Now, I can just try plugging in and so on. But I'd rather come up with a pattern. So now I need to look into the formula. And in fact, I'll do this. I'll write it here, the formula, so that it's easier to see. Okay. This is the B matrix, this is the A matrix. When I multiply them, I'm going to get a 2 by 2. It's going to have this formula. But I want to make sense of this formula. To understand this 2 by 2, all I need to understand is each of these entries. Okay? Let's first focus on this top left corner. How can I make sense of this expression? Well, this top left entry is the 1, 1 entry of the product. Okay? And the pattern is this. I'm multiplying a bunch of entries coming from A or B, and the outer indices are always 1, 1, whereas the inner indices always match. Okay? That means, really what is happening is that to compute this entry, the top left entry, the 1, 1 entry, for the left matrix, I take the first row, and for the right matrix, I take the first column. Okay? Then I zipper them up. What does that mean? Take this, multiply it by this, take this, multiply it by this. Then add them up. Put the answer, put the end result here. B11, A11 plus B12, A21. Again, to compute the 1, 1 entry of the product, I take the first row of the left matrix and first column of the right matrix. Okay? Multiply this by this, this by this. Then add everything up and put the result here. This is how I think about it. I don't go through this. This is how I imagine. So for instance, if I were to, I'm not going to go do all 4 of these entries, but for instance, let's try to do this as well. What is the idea? This entry now is the 1, 2 entry of the product. Okay? First indices are always 1, and the last indices you see here are always 2. The middle indices always match. Okay? So that corresponds to this idea. To compute the 1, 2 entry of the product, take again the first row of the left matrix and zipper it against the second column of the second matrix. of the right matrix. Okay? It's as simple as this. Okay? The challenge is to be able to do this efficiently and fast. Okay? The next problem set I'm going to release today, problem set 3, is going to be all about, computing a bunch of products and stuff. But it's as simple as this ultimately. Now you might disagree with me that it's not simple, but compared to other things that can happen, I guarantee you this is fairly nice. You can make a computer do this ultimately. Okay. Any comments about this? This is my idea. Now I'm going to apply it with the example. Okay. Again, like I said, you can try plugging the values into the formula, but you're not going to I don't remember this, but I have this story. Oh, left one, turn it into rows, right one, turn it into columns, and then mix and match. Okay? So what do? I'm trying to compute this product. Left matrix, I always split into rows, okay? Whatever the left matrix is, the matrix on the left. So think of it as separated like so. The matrix on the right, separated into columns. When you multiply two 2x2s, you're going to end up with a 2x2. Start with allocating your memory. Okay, that's your 2x2. Now you want to fill in the blanks. 1 entry, first row against first column. 0 times 2 is 0, plus 1 times 0 is 0. Okay? Here, I need to take the first row, second column. 0 times 0 is 0, 1 times 1 is 1. Okay? Here, second row, first column. 1 times 2 is 2, 0 times 0 is 0. And this is 0 also. Make sense? I don't care if your matrices are 5 billion times 10 billion, okay? This is always the rule. Now in practice, what is the case is that you don't want to do this because this requires, for high dimensions, a lot of compute. So people come up with a bunch of ways to not actually exactly compute this. There are certain structures and so on. But we're not going to get there for now. Our purpose now is to really understand how this linear algebra business works, how matrix algebra works. Okay? Now, I told you, matrix-matrix multiplication works pretty much like number-number multiplication. The only difference, so you can distribute over addition, whatever, all that stuff. The only thing you have to be careful of is the order in which you're multiplying. Everything else, you can just think of these abstractly as numbers. Now let me compute AB with the same matrices. Just do it here. Now again, remember, we did this example before, and geometrically we realized AB is not the same thing as BA. But algebraically too, you're going to see that they are different. So again, the same example continued. This time I want to compute A times B. Now I need to write them in this order, okay? Same rule, okay? You're not looking at the name of the matrix. You're looking at where you see it. A is now on the left. You need to split it into rows. That's always the rule. And the one on the right, turn it into columns. It's going to be 2 by 2. Let's do this fast. 2 times 0 is 0. 0 times 0 is 0. 2 times 1 is 2. 0 times 0 is 0, for instance. I don't need to keep calculating because I know at this stage already, for instance, AB is not the same thing as BA. But let's see, let's finish the calculation. 0 times 0 is 0. 1 times 1 is 1, and then this is 0. Okay? So they are different. Any comments or questions about this? In a second, I'm going to switch over to general matrix multiplication. Yeah, go ahead.
Isn't multiplication supposed to be like commutative though?
Just for numbers. That's the point. What your colleague is referring to is this idea of commutativity. Gets to commutes. Say, if 5 times 3 equals 3 times 5, you say, oh, these matrix number multiplication commutes. Matrix multiplication is not commutative. That's the sort of technical term. Matrix mult is it's not commutative. It's not important what this is called technically. Don't worry about it. All you need to know is that AB is not in general equal to BA. Now, on the one hand, this is a bad thing. You would rather not worry about the order in which you multiply. But also, somehow, this fact that AB is not in general equal to BA turns out to be just complicated enough that it models a lot of real phenomena. And indeed, you call the difference between AB and BA something. That is what is called the commutator, or the bracket. Okay? I'm going to ask you to compute a bunch of brackets in the next problem set also. Let me define it. This is not in the textbook, but I want to emphasize this, okay? You should not expect the so-called commutator to be 0. For two matrices, AB, their commutator, okay, or bracket, that's also a name, bracket, is, and this is denoted like this, A comma B in square brackets, while you compute AB and BA, and then you look at their difference. Okay? Which means that ultimately then matrices should be square and so on. And if you hear someone talk about commutation relations, they're really talking about, oh, you have these linear transformations relevant to their context, and they need to be able to do A first, then B, or vice versa, and somehow these not equal to each other. The extent to which you get the changed order is something important, okay? If it weren't important, people wouldn't be calling it things. So you should expect to be non-zero in general. Yeah.
So it's important the order.
Yes.
Things in the brackets. So bracket AB is always AB minus BA.
Say again.
So
The order is important in the bracket, yes?
because it's not an absolute value.
Yes.
A comma B is always AB minus BA. That's the
AB. Yeah, exactly. Yes, it's always in this order. Yeah, if you want to do some algebra, you can just take this to be for 2 by 2s. You have this, for instance. This is one of the most important identities. Well, let's perhaps first say this. A bracket B is minus B bracket A, because you just flip the orders. But also, the more complicated thing is this. BCA, so BCA, CA, B, bracket, 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 brackets, everywhere brackets. This is what is called the Jacobi identity. very important identity. Not very essential for our purposes, though. If you want to sort of do some matrices, lots of fun. So I want to switch over to the general rule for the matrix-matrix multiplication. Should I do an example or give the general formula? I'll give the general formula later. Let's do an example. So, okay. Let's take this. Say A is, well, let's just use 2, 1, 1, 1. And then B is -5, 2, 1, -3, 0, 4. Okay. I want to compute AB. Okay. The left one, turn it into rows. Right one, turn it into columns. Again, I'm going to use the same tactic. But you see, there's a problem here. I cannot just couple, let's say, this row against this column. They are of different dimension. This is not well defined. You cannot multiply this in this class. For now. Not defined. Okay. Remember, we were writing the dimensions of matrices. So A is 2 by 2. B is 3 by 2. When you write this, okay, 2, 3, 2. The middle numbers don't match. When they don't match, multiplication is not defined. Yeah.
But that would mean that BA is defined, though, right?
BA is defined.
Does it match?
Yes. Very good. That was what I want. That's what I'm going to do now. Let's first digest this. Okay. When you write these dimensions in the right order, the multiplication is defined insofar as this common number is the same. If it's not the same, it's not defined. Okay. I'm going to ask in the next problem set, is this defined whatever? But like your colleague suggested, the other way around, BA this time is defined. Again, I record the dimensions. B is 3 by 2. A is 2 by 2. And furthermore, I know that when I do this multiplication, I'm going to get a 3 by 2. The middle dimension is going to drop. You're going to have these two dimensions. Okay? Like this, times 2, 1, 1, 1. Left one, split it into rows. Right one, split it into columns. That's always what you do. Okay, that's the one rule. Right, so this time, rows are two-dimensional, and the columns are two-dimensional here too, so I can combine them. I'm going to end up with a 3 by 2. Okay, the middle dimension drops. Okay, this entry is -5 times 2 is -10, plus 2 is 8, -8. Okay, this by this, this by this. Add them up, put them here. This entry, this by this, -3. This by this, -1. This by this, -2. 4, 4. Make sense? What is the perhaps general formula in terms of indices? What you can say is this. Say A times B is this new matrix C, then the ij entry of C is defined like so. Cij is the sum, well, where k goes from 1 to, let's say, m, I guess. Let's say this middle dimension is m. A, I, k, b, k, j. If you're looking at the ij entry of the product, you fix the leftmost index to be I, you fix the rightmost index to be j, and then the middle indices, you run through all possible indices. Multiply, add them up, that gives you the ij entry of the product. That's the rule, if you want to be explicit. But again, like I said, I don't keep this in mind, really. Keep this in mind. Left one into rows, right one into columns. We have a couple more things we would like to be able to invert, matrices, and so on. We're going to talk about those on Monday. Thank you.